So today I would like to discuss about how to interpret machine learning models and increase transparency. Couple of words about me. I am a data scientist with more than 10 years of experience. I created about 100 of different models, and I love math. And today it will be a part of our conversation about Shapley values. So I worked in lead fintech companies in Russia and in the UK. So first topic will be a comparison of logistic regression and black box model. Why I think that it's important? First of all, because logistic regression looks like something which absolutely outdated. So how can we use it in 2023? But unfortunately, or maybe fortunately, a lot of very big financial organizations, a lot of big banks still use logistic regression in their daily work. And it's not because they're just so outdated by itself. Sometimes very clever people, like Codementor 10 PhD, can use logistic regression. And why they do it, and why all these banks don't like black boxes. So first of all, logistic regression is something very, very simple, very basic. It can be described easily by this formula. It's a sigmoid of some linear combinations of some features. And it's quite obvious, for instance, from this particular formula, that if I presume that all these features were normalized previously and all these features are in the same range, approximately in the same diapason. So it's quite obvious that first feature is very, very important, and the third feature is maybe it's just a noise, and we can even exclude it from our formula. So it's one of the reasons why we use logistic regression. From the formula of logistic regression, it's very easy to understand. When we found these confusions, it's very easy to understand what feature is most important, what is less important, and what all our model is about. So it's also quite easy to explain this to internal or external audit. So external audit is maybe even more important for big financial institutions like banks, because they all had to submit their models to central banks, at least, and many other audits. So logistic regression in this case, it's like lingua franca. It's so basic that everybody knows what is it. And in many cases, quality can be quite satisfactory. However, it's very simple, and in many cases, its quality is not satisfactory at all. For instance, in our case, if we have x, for instance, factor feature x2 can be 0, and we have one behavior, and x factor x2 is 1, and we have absolutely other behavior, it's impossible to describe this behavior by logistic regression. And it's bad. It can lead to very substantial underfitting. So the black box is the opposite of logistic regression. In case of black box, we have just input and output, and something inside. And it can be not a real black box. It can be some kind of gray box. For instance, it can be a boosting with 1,000 of different trees, and each tree can have 10,000 of different leaves. And we can look at this tree and look at these leaves, but really it's absolutely impossible to understand what it's all about. Yes, because it's impossible for a human being to understand such a big amount of information. So what is the downsides of black box? It's not obvious what feature is most important, and it's quite important why it's bad. Because if some feature is very important, maybe we can invest more money to get this feature more precisely. Maybe we can, for instance, create some other feature. We can understand, okay, our data is dependent, our label is dependent from some particular set of data, and maybe we can create some different features connected with this important feature and increase the quality of our model. And in the opposite way, maybe we have 1,000 features, but only 10 of them important, and it means that we can exclude this 990 features. So it can be a significant improve in amount of data which we need to gather for our model. And again, for black box, it's impossible to do case analysis. For instance, we have some cases where we think that model have to be triggered, but it was not. And we think why it was. And then for black box, we just know that it was not triggered, and that's all. And it's very, very bad situation. We cannot improve this in any way. It's difficult to understand how features interact with each other, and it's all impossible to explain it to external audits that, okay, this black box is very good black box. We don't know why, but it's very, very good. So, however, black box can provide extremely good quality of predictions. What is the point of today's lecture is that it's impossible really to improve the quality of prediction of logistic regression, at least significantly. But we can make, we can at least try to make black box much more transparent, and we can try to explain it to all these audits, to our management, etc. So, first thing which you can use for this is feature importance. Feature importance is a special technique which shows us what feature is more important, what feature is less important. When we calculate feature importance, we got something like this. It's how feature importance for LightGBN looks like. Feature importance, it's allowed to understand what feature is more important, what feature is more important, what feature is less important. It can give us some intuition about our data and how can we create, how can we design more better features for our data, from our data, and give us some ideas which features are totally not necessary. For instance, if importance of features about 0, we can try to exclude them completely and build a model without this feature. However, it does not allow us to make case analysis in every particular case. So, from my perspective, there are two different groups of feature importance. It's model-based feature importance and data-driven, dataset-driven feature importance. It's, from my perspective, there are a huge amount of them, maybe thousands of different ways to create feature importance. However, model-based feature importance, they are driven by model of or process of model creation. It's easy to calculate. In many cases, we calculate this during the creation of the model. but it doesn't show the feature importance on new dataset, and doesn't show feature importance in every particular case. I will give two most important from my perspective examples here. It's split feature importance. It's when result contains number of times the feature is used in the model. So we have again this gray box boosting with 1,000 of different trees, every tree with 10,000 of different leaves, and when we do every split, we use some feature, and we can just count that this feature we used overall like 2,000 times, but the other feature is 20 times. So this feature which we use 2,000 times, it looks like much more important that this which we use 20 times. So the other example of this model-based feature importance, it's information gain feature importance. For instance, in LightGPM package, we calculate this information gain feature importance automatically. It's when we do any split, when we try to build the model, when we do any split, for instance, we can have information gain criteria. It's we try to decrease the entropy. And the result of this decrease is like how we decrease the entropy because of this feature. And every time when we decrease the entropy, we like sum it, and the overall information gain which we got by this particular feature is the feature importance for this feature. So again, it's very easy to calculate, and but it doesn't show the importance on a new data set. So maybe for other data sets, not for train, it can be quite significantly different. Performance of the model and importance of the feature in different data sets can be significantly different. So the next step is data set dependent feature importance. They are driven by data sets and it can be difficult to calculate them. We don't calculate them automatically when we build the model. And of course, it doesn't show feature importance in every particular case. Two main most important examples. It's loss function change feature importance. It's when we try to exclude feature by feature from the model. So we do all the same steps in the model except for this particular feature. So we just completely exclude some feature from the model and look at the loss function and on the data set. And if the difference is big, so the loss function is supposed to increase without this feature, it means that this feature was important. If we have approximately the same loss function, it means that this feature was not important. And my favorite one is permutation feature importance. It's when we take some data set, calculate some error like loss function or something, some other error on this data set by this model, and then we start to permutate. So we take one feature and replace values. For instance, value of this particular feature from case 1, we replace on value of this feature for in case 21, etc. Replace them by places. So if this feature was not important in our dataset, it will change to the same error. But if this feature was important, it can change the error very significantly. So again, this feature importance, dataset dependent feature importance, we need to calculate them in every particular case, and it give much more sensible information from my perspective, but we need to calculate them. Sometimes it will take maybe several hours to calculate them, in contrast to model dependent feature importance. Okay, so it's about feature importance, and it's quite important instrument, but I would like to tell you about more interesting, from my perspective, more interesting alternative for this. 1 second. Okay. Okay, I would like to tell you about more important alternative for feature importance. It's Shapley and Shap values. So the main disadvantage of feature importance is that we cannot do case analysis. So for every particular case, it's difficult to understand what was really a real driver of this particular case. For instance, you have several examples when your model definitely have to be triggered from your perspective, but it was not, and you try to understand why. So, and in this case, we can try to use some idea from math, from game theories. This idea called Shapley values. So really, it's the formula for Shapley values. It's on the top. It's quite. It looks very strange and difficult, but really there is very easy explanation for this formula. We have let's imagine the situation when, for instance, we have orchestra. Like some can play on guitar, some can play on drums, some can play on I don't know, piano, play piano, and altogether they can earn some of money. But they can try to earn some money by themselves, or piano with drum without guitar, etc., or guitar with drum. So they can earn some money separately, and they can earn money altogether. And let's imagine then they decided to earn money altogether, like orchestra, and now they need to split this money between them. Like give some money to someone who played guitar, someone who played piano, someone who played drums. So how can they split this money? How can they share them? There is an idea that if we have these four properties, the only answer is the formula on the above, Shapley values. So these four properties, first, it's literally means that they try to split the money which they earn altogether. The next one means that if we have two people in this orchestra which contribute exactly the same, they have to get the same money. The last means that if someone is completely useless, he have to get nothing. And the third, it means that if we have two independent games, so they can earn like orchestra, and maybe and some other game they can earn like, I don't know, like waiters. Who knows? It means that these games are independent. If you earn something in the first game and other games, the total money which you get is the sum from both of these games. So if we satisfy this 4 simple and really quite obvious properties, we will have this formula on the above. And let's try to look at one example. Maybe it will help someone to understand. So let's imagine that and Alice can earn $200, Bob 100, and they together can earn $1,000. So how they have to distribute this $1,000 if they work together? So from Shapley perspective, separately they can earn $300, and it's the synergy of the coalition. It's 1,000 minus this 300, it's 700. So it's the synergy. It's in Shapley work. It's called the synergy of the coalition, and synergy of the coalition we should divide equally between everybody. So Alice will get 200 plus 350. So it's the half of 700. So Alice will get $550, and Bob will get 100 plus 350. It's $450. So it's like example to give some intuition about these Shapley values. So we supposed to calculate the synergy of every coalition, and on top of coalition, and divide every synergy between the member of this synergy. So how can we use it in our cases? Let's imagine that we calculate like a score for we have 100, maybe even 1,000 of features, of different features, and we have some final score. And we try to understand what was the contribution of each score to this 1,000, to this final score. So this final score is like this sum at the end. And we try to, and we can use exactly this formula to calculate the contribution of each this feature. Each this feature is like a player, and and the final score is together work, and we can use this formula to calculate the contribution of each player to this final score. So it's quite interesting approach, and it really works on practice. However, it's very difficult to calculate all these Shapley values directly, because we need to do a lot of calculation, and we need to calculate all different permutations, and it's very, very long process. So really, it's for real life examples when we have not like 10 features, but 100 features, 1,000 features. It's computationally very difficult, at least for many cases. And but there is an approximation of Shapley. It's Shap values. Shap is Shapley additive description, as I understand, as I remember correctly, Shapley additive description values. So it's a linear approximation of Shap values, and we can calculate these Shap values quite fast and effective. So, for instance, for 1,000 of different features, for 100,000 of different cases, we can calculate it in less than 1 minute on quite ordinary computer. So it's and we can really use these Shap values in our data science work every day. I personally use Shap package. It's most effective from my perspective. And what is this? It's a picture exactly from the website. So we have this black box, which we talked about previously on the left. and we have age, sex, some BP, BMI contribution, base rate, it's average meaning of our prediction, and output 0.4. And we use this Shap for its a particular case. So there is a particular value for this features. And now we can look and see that BMI it's 0.1, BP is 0.1, sex is minus 0.3, and age at 0.4. And for instance, we can say, oh, why maybe in this case model was triggered, and we say why it was triggered. It's almost never was triggered for females. But we can say, yes, of course, it was. It shouldn't be triggered by female, but the age is 65, so it was triggered. I hope it's something good happens here. I don't know what is this model about. So we can get this picture, and we can get these particular values for every case. And in this case, we can make case analysis. Yes, we can look at this particular case and understand what feature contribute, and why the model was triggered and was not triggered. So what we can do by Shap values? We can understand the impact and importance of every feature. So we can do exactly the same which we do previously by feature importances. We can understand the impact and importance of every feature on any data set, like, and in any subset of this data set, really. Also, we can analyze any particular case which is very important. So, like, we have, I don't know, the business said, okay, why we was not triggered in this particular 20 cases, and we can give them exact explanation for every case or for case altogether if it was one reason. If we believe that some set of features connected with some typology, we can calculate the impact of this typology in overall score. It's quite unusual, but we really can do something like this. So, for instance, I don't know, we think that this set of features is, for instance, we can identify some crime. And like all these features, it's for any crime, and some subset of features we believe it's connected with drug trafficking, and the other set of features connected with mostly with human trafficking. They can overlap, but we can say, okay, these features is connected with human trafficking now were really a big driver for the overall score, and this connected with human trafficking was not driving. The impact was about 0. So it's more likely like drug trafficking, for instance. And we can, if we believe, I don't know, that some set of features connected with some particular customer, we can classify. Yes, we can say that, okay, this model was triggered, and we think that we get some additional information that it was triggered, and more likely this is connected because with this particular type of customer. So we have a lot of advantage by these Shap values. So, conclusion. The conclusion is the same from very beginning. So it's impossible to improve logistic regression, and we cannot make it more sophisticated because it's basic from by their nature. But we can, by using these Shap values, feature importance, we can interpret our very complex model, our black and gray box, and get some intuition about impact of every feature. And we can use all these instruments to get our black boxes more transparent and as a result, we can explain the stable, reliable instrument, and we can use it in our daily work. We can explain it to our management, internal, external audit, etc. So I believe that it's possible to get rid from logistic regression one day. Okay. Thank you. Does anyone have any questions?
Hi, how are you? Hello?
Hello?
Hi, Artem. Thanks for the beautiful presentation. I really enjoyed. I'm following closely to it. There's a particular section where you talk about computational expensivity of the Shapley calculation. You're saying in Python it might be expensive to compute that. So maybe you know the variant of the Shapley equation, which is used in Python so that the computation is not very expensive.
But as I understand, exponentially increased, dependent on the amount of features. So for, I don't know, for 1,000, for 10,000 features, it's, from my perspective, it's almost impossible to do all this calculation. So I mean Shapley calculation. But Shap, yes, we can.
So like Python uses the exact equation you presented, or it uses a lightweight version, that package you presented. Is it using a lightweight version or the exact equation you presented? Just to ask.
What Python package do? Python package uses Shap calculations.
Okay.
Sorry, I'm not sure that I understand.
All right. No, I think I'm fine. Thank you so much. Hey, would you also have recommended references, maybe for one to familiarize himself with the background and the literature behind all these Shapley computations?
Sorry, you want some package which really make this Shapley computation, not Shap, but Shapley, yes?
I'm actually referring to references you might have, which may provide one with more reading, so that I'm familiar with the background, because I'm new to this Shapley computation. I only know the importance computation from like ensamples and all these kind of tree-based algorithms. But the Shapley package, I'm not used to it. So would you have some references maybe where I can read some more?
Okay. For instance, I put it into chat that this very good article about using Shap values. Or you can look at this the package which I always use for this Shap computation. 1 second.
Oh, thank you so much.
You can look at them and say, really by them you can, by this package you can, I believe, compute both Shap and Shapley. But Shapley is really expensive, like, I don't know, for my cases it was like 1,000 times slowly than Shap.
Oh, I see. If you have had some more time, working with Shapley package, with 85. I've heard some people talking about 85 package in Python.
Oh, 85.
Or is it the same thing or something?
I believe that the result will be approximately the same, but I personally use this package. You mean alternative for the whole approach or alternative package for the same approach?
Oh, okay. That's right. That's right. Thank you so much.
Okay. One second. Question. It were on device synergy collision by two. Modest individual earns contributes. It were Johnson, thank you. One more question from you. You know, like about this synergy of collision. Here the Alice earn 200 and Bob can earn 100. So the synergy of collision is the difference between how they can. So if they will work separately, they earn 300. Yes, but the synergy of the collision is how much they can earn on top of this. So it's 1,000 minus 200 minus 100, so it's 700. And this Shapley approach, we need to split this between them equally, because synergy, they belong to both of them. If Bob refused to work with Alice, Alice also will lose the synergy. So we need to cut the synergy equally between them, or if it will be synergy for three of them, we will divide the synergy to three parts. So all this Shapley approach is to calculate this synergy between different collisions, like on top of each other, and then divide them equally between the members of these collisions. So Alice, yes, she can earn more, but she finally got more. She got 550, and Bob will get only 450. So the difference in 100 bucks is still here.
Thank you so much. No, that's clear. Thank you so much. Artem, do you have maybe some open source, maybe GitHub or repo to check around where you have used these techniques? Or maybe you will hang around on LinkedIn as well, sharing the same stuff?
GitHub, unfortunately, don't have GitHub. I have some examples.
Okay,
you can send me, connect with me on LinkedIn. I have my LinkedIn at the end, and I can send you like the file with example.
Wow, thank you so much. That would be great. I really want to learn this thing.
Yes, it's very useful technique for case analysis.
Yeah.
So it's okay. My LinkedIn is strange that it's not. And 1 second. On our chat, I will add my LinkedIn. I'm not sure that you can see it in my profile.
Yes, now I can see the link. Now I'll shoot you a request then. Thank you so much.
Oh, you're welcome. Okay.
Artem, this is Pierre Du Bois. Just wanted to say thank you. I didn't get a chance to see the whole presentation. I apologize a little bit. I kind of came in a little late, but thank you for sharing that article on Shap values. That is, I think between that and your video, that will help me out at my end a little bit. I'm just still kind of learning a little art programming, but I like gathering information. It looks pretty good, so I look forward to digging in. And just want to say thank you.
Oh, yes, you're welcome. It's a pleasure to share something. So I'm very glad that you, if you will use it. Okay. So I don't know if nobody have any questions anymore. I think maybe we can. Do you have any more questions, some of you?
Well, on my side, I don't have. Just to say thank you as well for the wonderful presentation. I've learned a lot.
Thank you for for visiting, for attending my presentation. Okay, so I think that we can finish now. So thank you for attending today, and I hope it's all will be useful in your job. So, okay.